Sometimes you can't measure the heat of a reaction directly using calorimetry or even indirectly using Hess's law. Sometimes you have to just resort to approximations using bond energies. So in this video, I'm going to explain to you how to use bond energies to get approximate enthalpies of a reaction. So a few things about bond energies, first of all. The first thing that you need to know regarding what a bond energy is that it's the amount of energy required to break 1 mole of bonds in the gas form. And you'll probably need to refer to a table of bond energies to do these calculations. Bond energies are always going to be positive because it always requires you to put in energy to break a bond. The reverse is also true. If you're forming a bond, it will release energy. So those same bond energies then become negative when a bond is forming. Molecules with high bond energies are usually more stable than molecules with low bond energies. It means that it's more difficult to break those bonds with high energies, so they're more stable molecules. Single bonds generally will have lower bond energies than double bonds or even triple bonds. So let's just take, for example, chlorine and nitrogen. So chlorine gas has a single bond. If we were to draw just a really quick, crude Lewis structure for chlorine gas, it's diatomic, it's Cl2, so chlorine bonded to itself. The amount of energy it takes to break that single bond is 243 kilojoules per mole. Now, if we compare that to nitrogen, N2, which has a triple bond, the amount of energy it takes to break that triple bond is 946 kilojoules per mole. So we can see that the stronger the bonds, the double or triple bonds are going to be stronger, the higher the bond energies. Now, bonds with larger atoms will have lower bond energies than bonds with smaller atoms because those electrons are held closer to the nucleus. So it requires a lot more energy to break those bonds. All right, let's take a look at how we can practice using this idea to get some approximations for heats of reactions, for different types of reactions. And they work better for simpler, smaller reactions, so that's what we'll be practicing with. We're going to use bond energies to approximate, to calculate the heat of reaction for the combustion of hydrogen gas. Now, just a real quick prediction here. I predict that it's going to be exothermic because most combustion reactions are exothermic. First, I will write out my equation. So H2 plus O2 in a combustion reaction gives us H2O. The next thing I'm going to do is balance this equation. So 2 moles of H2 react with 1 mole of O2 to give me 2 moles of water. Now the next step involves going back to Lewis structures. I'm going to be drawing the Lewis structure for each of these molecules because what I'm interested in is what is bonded to what? What atoms are bonded to each other? So I have these 2 hydrogen molecules, the 2 H2s. I have 1 oxygen molecule. Remember, it has a double bond. And then I have 2 water molecules. So I'm really interested in what bonds are in my reactants and what bonds are in my products. So in the reactant side, we're going to be breaking all of those bonds in the reactant side. So I'm going to be breaking the hydrogen bonds, breaking the oxygen bonds, and I want to know how much energy it takes to break all of those bonds in all of the reactant molecules. Well, a hydrogen bond, an H to H bond, requires 436 kilojoules per mole to break. And I have 2 moles of that. So I have 2 times 436. An oxygen-oxygen double bond, if you look up on your bond energy diagram, you have 498 kilojoules it takes to break that oxygen-oxygen double bond. So if I add these 2 numbers together, I'm going to get the total amount of energy that I have to put in to this chemical reaction to break every single one of the bonds. So 2 times 436 plus 498 gives me 1,390 kilojoules. That's how much energy it takes to break all the bonds in all of the reactants in this equation. Now let's look at what bonds are forming. I have 4 bonds forming, and they're all between oxygen and hydrogen. So I have 4 bonds, and because they're forming, the bond energies are negative. So the bond energy for an OH bond is 464. Now we're forming this bond, so it's a negative 464. And there are 4 of them, so it's 4 times negative 464, which is negative 1856 kilojoules. So I have all the bonds being broken, all of the bonds forming, and I'm going to add these two numbers together to get my approximate heat of reaction for this reaction. So 1370 plus a negative 1856, type it in your calculator, and you get negative 486 kilojoules. These are all units of kilojoules per mole. So you'll see I kind of left some of the units out, but let's just remember it's kilojoules per mole. Now, one thing I'm going to show you here is how we can kind of diagram the energy for this reaction. So I'm going to make an XY plot here. On my Y-axis, we're going to start at 0. So this is kind of like the beginning of our reaction. We haven't put energy in, we haven't gotten energy out. We're starting at kind of a clean slate here. So we're going to start at 0. And I'm going to have energy on my Y-axis. I'm going to represent energy in kilojoules. So the amount of kilojoules I put in or take out. My X-axis is going to be time. So as the reaction progresses, what's happening to energy. So the first thing that happens is I have to put energy in to break all those bonds. We represent putting energy in by an uphill. And I'm putting 1370 kilojoules into this reaction to break all those bonds. I'm going uphill that amount. Now, once I break all those bonds, I'm going to get a whole bunch of energy out because so many bonds are forming. The amount of energy that I get out is 1,856 joules. So that's downhill, that's negative. I'm getting all of that energy out. 1,856. Now the difference between the two is the difference from 0 to however far down it goes below 0. And that's the amount that when I added the two numbers together, how much I got. So negative 486. So because I got out more energy than what I put in, this is an exothermic reaction, which is what I predicted. It's also a negative heat of reaction, the delta H of reaction. The delta H is a negative number, so I can show that this is an exothermic reaction just by getting that negative number there. And I can also show it graphically by showing that I get more energy out than what I put in. I have to put in that energy to break the bonds, and I get out energy when bonds are forming. So pause the video and try this one. All right, we're using bond energies to estimate and calculate the heat of reaction for the synthesis of ammonia gas, which is NH3. And this is a synthesis reaction, so I put in N2 and H2 and I get NH3 as a product. Now I wrote the reaction. All I need to do now is balance this equation. So I get, we have 2 ammonias that are being produced, requires 1 mole of N2 and 3 moles of hydrogen gas. The next thing I want to do is draw out the Lewis structures of these molecules because I want to know which bonds specifically are breaking in the reactant side and which bonds are forming in the product side. So I have my my N2, my 3 hydrogens, and then I'm forming NH3. I'm forming 2 NH3s here. I'm leaving off lone pairs of these Lewis diagrams because the lone pairs are not needed to show the bonds. If you want to put the lone pairs in, that's totally fine, just to make sure that your calculations add up. That's totally fine. I'm just cutting a little corner here because it's not necessary. So I need to break that nitrogen bond. That's a really, really strong bond, which requires a lot of energy to break, 946 kilojoules to break that one bond, 1 mole of those bonds. And then I have 3 hydrogen bonds that need to be broken, so that gives me 436 times 3. And if I add these two numbers together, 946 plus 3 times 436, I get 2,254 kilojoules to break all the bonds in these reactants. Now I'm forming bonds to make the products. I'm going to be forming 6 bonds, 6 NH bonds. So this is a negative number because I'm forming bonds. So 6 times negative 389 gives me negative 2,334. So all the bonds that you're forming get that negative value because it releases energy when a bond is formed. So if I add these two numbers together, I get 2,254 plus a negative 2,334. This is an exothermic reaction. It's going to end up being negative. I get a negative 80 kilojoules. So I get just a little bit of energy out of this reaction. I put in a lot of energy and I get a lot out, but I get just a little more out than what I put in. So let's diagram this. So I'm going to start at 0. 0 is going to be kind of like my even point, my starting point, my clean slate. And I'm going to put energy on the y-axis and time or reaction progress on the x-axis. It doesn't really matter what you put on the x-axis as long as you can show what's happening as the reaction progresses. So starting at 0, I put in a lot of energy to break all of those bonds. I'm breaking 4 bonds in this reaction. I put in 2,254 kilojoules of energy to break all of those bonds, and that requires me to put that energy in, and then once that energy is put in, I get a whole bunch of energy out to form those 6 NH bonds. And the amount of energy that I get out is 2,334 kilojoules. So that's that difference. That's the downward hill there. I get that much out. And the difference is negative 80 kilojoules. So this is an exothermic reaction with an overall difference of 80 kilojoules. That means I get 80 kilojoules more energy out than what I put in the first place. So this is an exothermic reaction. Now, just to show you, to contrast here so you can see what an endothermic reaction looks like, I'm just going to sketch a real quick endothermic reaction here. If we start at 0, we have energy on our y, time on our x. Let's just say that I put in 100 kilojoules, okay, just for ease purposes. I put in 100 kilojoules of energy, and let's just say that I get out just a little bit of energy here. I'm going to get out 30 kilojoules of energy. So if I put in 100, but I only get back 30 from the bonds being formed, then overall I have a positive 70 kilojoules for my delta H, or my heat of reaction. That means I have to put in, or I lose, I guess, because I'm putting in a total of 70 kilojoules of energy to put into this reaction so that the reaction can go. And I get very little out. I get that 30 kilojoules out. This would be a diagram of an endothermic reaction.